So I'd like to introduce the second speaker and the final speaker of this section, Alex Tait from NIST, and I'll let you take over.
Okay. First, we gotta find wherever the slide went. So I am a postdoc at NIST, working with Seiwu Nam and Rich Mirren. And I want to thank the organizers for having me. And the program says Princeton. I did my PhD in Princeton, and I'm giving this presentation as a private citizen. How do you do this here?
Full screen for you.
There we go. So, but I'm still going to be talking about some of the work that's going on in NIST. That doesn't work. But I'm going to start with something a little metaphysical. Is nature predictable? And so if you went to school after the 30s, you'd say, no, the quantum theory, quantum randomness, and we have this math and it describes our experiments. But there are other theories, in terms of local realistic theories, that say there's something beneath quantum mechanics that is deterministic, that just explains this seemingly random thing that we see. And so Einstein is quoted as saying, God does not play dice. That's kind of an expression of this. So I kind of lied. It's not metaphysics. You can actually test this. You can test local realism in an experiment called a Bell test, where you entangle two particles and separate them far enough so that they cannot influence one another without violating the speed of light. And then over multiple measurements, you look at the correlations between their states. And local realism predicts that there's a limit to the correlation. So if you measure more than that, you have violated local realism. This was done in these three papers 40 years after it was proposed, within a month of each other. And this means that this experiment can generate randomness that provably could not have been known by any entity, even if they had complete knowledge of the state and history of the universe. So we call these God's dice. So why? Besides answering this pretty big question, this is useful. Generating random numbers is kind of the first step in a lot of cryptographic protocols. And if your generator can be predicted somehow, your encryption may not be secure. And so NIST actually puts out, oh, this one works. Yeah, they publish random numbers that are, I'll just say very random and provably unpredictable, which is important. So in order to do this experiment, and where I'm kind of getting into my main talk here, is that you need to detect 2/3 of photons. Otherwise, you can't prove that you violated the inequality. And this is part of why it took so long to do the experiment, is that we need this efficiency. Now for linear quantum computing, where you're doing boson sampling or getting nonlinearity through the detection, you're not just detecting 2 photons at a time, but maybe 10 or more. And so those efficiencies compound, and you need very, very high. Quantum communication, any photon lost is bad because you have to make up for it with error correction, which kind of either is a hardware problem or introduces some redundancy. So I'm going to start by talking about single photon detectors at NIST, and then some recent work we're doing on integration and co-integration specifically, and then get to neuromorphic photonics and links with quantum information photonics on silicon. So some of the things we do at NIST in our group is we do basic science and try and improve the behavior of single photon detectors. But we also improve how well we can characterize single photon detectors, because when you get to very high efficiencies, the error tolerance matters, and it's actually active research there to try and reduce that. And then we also want to get the knowledge that we gain and the technology that we create out to the public, that it fits in with kind of our mission at NIST, which is to impact science and technology, not just do science. So, for example, if you're making a single photon source and you want to characterize it very precisely, you can just email us, and you can talk to us about that. So we talk about two types of detectors. One is the transition edge sensor, and it's just an absorber that takes an energy and that changes its temperature. So if it's superconducting, there's this very sensitive transition from normal to superconducting to translate this small temperature change into a larger resistance change. And this is what you see coming out of a TES. These curves, or these bundles of curves, appear when you put in pulses because the pulses have some integer number of photons in them. And there's a big difference between 1 and 0, which is very nice for rejecting dark counts. And these are some of our most efficient detectors, so about 80%. And so part of our work is getting them more efficient. Part of them is getting the measurement more accurate. Because you can see if we were on the upper edge of this standard deviation here, we're above 98, getting to 99%. And is that the case? Well, we need more accurate measurements to tell. So that picture didn't show up at all. All right. I can use this one. So a superconducting nanowire single photon detector is over here. This is another type of detector. And this meandering wire in the middle, colored blue, is carrying a supercurrent. So when a photon hits it, it breaks Cooper pairs, and this kind of funnels the supercurrent around this hotspot, what's called. And eventually the whole wire goes normal across its width. So you have something that goes from 0 ohms to kiloohms of resistance in here. And this is one of the packages that came out of our lab, and now you can buy these devices packaged from these companies, and they're here. And this is an important part of total system efficiency, not just like the theoretical efficiency here. And there's no secret in this design. Like if you want to learn how to make them, you can also just contact us. So next I'm going to move to silicon photonics. And one of the nice things you can do with SNSPDs is integrate them onto waveguides. So you have this nanowire meander on top of this silicon waveguide, and light going in gets absorbed, and it is sensitive to single photons. So this is a microring spectrum, but this is not transmission through the circuit. This is counts that we're getting on these detectors that are on chip. So if we're working at cryogenic temperatures, a funny thing happens is that these non-radiative recombination pathways in silicon that make it very, very difficult to make a light source, well, they kind of get inhibited. And you can bombard silicon to create defect centers that have optical transitions, and these will actually show up if you're working at cold temperatures. So some of the work that we've been doing lately is trying to optimize the brightness of these emissive centers. And this is work with Pops at SUNY Poly. He's fabricating 12-inch wafers that he sends us, and we take a picture with it and then dice it up and put them in the cryostat. And we've gotten some recent improvement. We're trying to optimize. I don't think we're done optimizing yet, so this is kind of in progress work. And the other thing that we showed is this co-integration of the LED with SNSPD. And this is important because now you have an optical circuit on chip in a cryostat with electrical in and electrical out. There's no fibers needed to measure these devices. Just one other device thing that we're working on are the superconducting amplifiers. And the idea here is to take millivolt signals coming out of detectors or other types of superconducting circuits and boost them up to volt levels, what you need to drive semiconductor-based transistors. And if you do this on chip at the low temperature, you just are more resilient to noise. And the nice thing about these, there's no Josephson and junctions. They're really easy to fabricate. It's like 3 liftoffs. And so what we're doing now is putting all of these things together. The detectors, sources, passives, and amplifiers. And we want to make this process open to the public because we think it has just general uses as a cryogenic silicon photonic platform. And we're planning to do this in a multi-project wafer format, like on a prototype scale, where we are fabricating in our clean room on 3-inch wafers. We're going to have an open source PDK, which will go online soon, hopefully. And then we're also making tools for basically Python-based EDA, open source tools like K-Layout and Fiddle. We were kind of developing for those and also developing our PDK to work best with those. But I mean, of course, you can do whatever tool you want to make a GDS. But we've looked into some more complex systems on this process here. And so this is not just an array of SNSPDs, they're all part of one system, connected together. So to do something like this, you need high yield and this electrical in, electrical out. And so Sonia fabricated this, it's called a HYDRA, or high dynamic range detector array. Oh no, that also didn't come out. So imagine here that there are dots falling on a line. Let me just open the PDF, sorry. Thank you. Here you go. Yeah, that's better. So, what this means is that each one of these splitters and each one of these detectors is pretty repeatable performance. And then on this wafer, I think she measured 36 SNSPDs and all 36 worked. So this repeatability is important if we're talking about larger systems here. So just an example of what you might be able to do on this platform. If you take a silicon microring here and then pump it on one of the resonances, there are various ways to create entangled photon pairs that are different wavelengths, different orders of resonant modes in the microring. Then you can split them apart using typical filters and send them where they're going. So what we would hope to see out of this platform is that all of this on this slide would be on chip. So that could be quite interesting, we think, for a lot of quantum information applications without having to deal with fibers going into your cryostat. But also, we're having some thoughts further ahead in terms of single photon sources in particular. Our group does a lot of fiber, entangled sources and single photon sources. And so we're particularly interested in that direction, possibly looking into quantum dots down the line using these emissive centers. Yeah, and so part of the reason why we want to open this up is we don't have the bandwidth to look into all of these possibilities. And so right now, it's not going public immediately. We're looking for collaborators to do process development, device optimization, people who would like to get early versions of the sample and know what to do with the samples, essentially, in terms of measuring them and having ideas of what to design, reporting characterization data, that kind of thing. Okay, so we actually originally were developing this co-integration platform to make a neuromorphic photonic system here. But just to introduce this, neural networks are this distributed kind of computing model. People use them a lot for machine learning nowadays. And then conventional computers are centralized, so they're very bad at evaluating them. So people have gone and made neuromorphic electronics, and these are CMOS chips distributed on a hardware level. They're much more energy efficient at evaluating distributed models like neural networks. But they're still electronic, and their communication is a big part of interconnecting all of these neurons together, and so this becomes a high cost in electronic circuits. So to do better with communication performance, you can use light, and if you're really going for the best possible efficiency, you'd communicate with single photons. And that's the idea behind this superconducting optoelectronic networks platform, or SON. And the neuron here consists of an optical to electrical to optical chain, shown with the components that I showed all co-integrated before. And then in the optical domain, there are these interconnections. This one is a 10 by 10, for example. So when you reduce power dissipation, this lets you get a higher ultimate scalability. Because if you take CMOS chips, for example, and stack them, the ones in the middle won't be able to dissipate their heat, and it'll melt through, basically. But with these, you can pack them in densely, and they're not generating very much heat. Now, of course, you're using power for your cryostat, but that's not really, the primary goal here is the ultimate scalability that we think is possible with current or foreseeable technology. So at the same time, in parallel, there's another approach at Princeton, which isn't necessarily looking for the ultimate minimum of energy efficiency. It's aiming for foundry compatibility. And there's actually a lot of similarities in the neuron. It's an optical to electrical to optical chain using a microring modulator. And the reason for doing this is that you don't need nonlinear optics because the electrode-to-optic transfer function is very nonlinear. So it's much easier to handle. You don't need to worry about dealing with the Kerr effect. So in these, so the interconnects are configured by microrings, which are tuned on and off of different signals to redirect how light is going through this, like from neuron to neuron through the network. So in both cases, of course, we're always thinking, what's next for scalability? And when you get to large neural networks, they tend to be hierarchical with lots of short-range connections and fewer long-range connections. And we think that optics will do well at this because it does well with long-range communication. But then there are a lot of practical challenges. How are you going to design a chip-scale system? Or what about a wafer scale? How are you going to control these things? Well, it turns out that some of these problems are shared by quantum computing with silicon photonics, because they're the same technological platform. They're both large-scale information processors. So these three big problems here we actually get for free because silicon photonics already has those. But so why is silicon photonics how it is? Is it demand for quantum computing? No, it's demand for cat videos. And this creates a lot of data center traffic, so much that they need fiber optics, and they needed a way to create lots of very cheap transceivers for their fiber optic links. So this is actually important. This situation where you have a robust industry is unprecedented in the history of optics. So we have this great platform to work on. But where it's going to get hard is when the needs of large-scale silicon photonics start to depart from those of data center silicon photonics. And there's some partial overlaps here. I won't go into these because, it's lunchtime, but we think that these are kind of things that you wouldn't really need for datacom that all need to be solved together. So in order for, quantum or neuromorphic computing to really flourish on silicon photonics, even though they're totally different theory, they kind of have to work together on a lot of this process technology. So just picking out a few points, these large-scale information processors have a lot of similarities in terms of platform challenges. We've shown a co-integrated platform for quantum information processing. This is going to be opened to the public, but right now we're looking for collaborators actively who are interested in getting some chips and testing them out. And more broadly, our group at NIST is trying to just advance the science and metrology of single photon detectors, also the applications and availability of them. So this is the team at NIST. We all do different stuff, so if you want to measure your single photon source, it's one person, or et cetera. But if you just email one of us, we can get you to the right place. Or for the time being, you can reach me here. Yeah, thank you.
Thanks, Alex. So we have time for a couple questions before lunch.
Very nice talk, thank you. I was curious, you mentioned a lot of things you're integrating, including sources, and if I recall, you'd mentioned an LED source. Is there any plans to do a laser source integrated as well?
Yes. So by putting an LED in a cavity, in principle, you can make a laser. And so we're investigating different types of cavity structures and looking at the best way to do that in terms of, so something we'd be interested in is like narrow line width in this case and high power. I don't have a backup slide, but if you want, we can talk offline about that too.
What type of temperatures were your amplifiers operating at?
They are using a tungsten silicide nanowire, so they need to be at 1 Kelvin.
Okay. And also, would you be able to go back to the areas of collaboration slide?
This one?
Yes, perfect. Thank you.
Any more questions? Okay, well, let's thank Alex one more time.
Thank you.